Thank you all for coming. First, I'd like to ask you all one question. How would you build a robot that finds the fastest way to the center of a maze? Now, unfortunately, in this world, nothing can be this simple or this easy. At least most people won't like it. But for most of us, especially engineers, we're going to have to do a bit of thinking and a bit of problem solving to get to the solution. Now, to get there, you might ask yourself a few series of questions pertaining to a maze-solving robot, like how does the robot turn left? How does the robot turn right? How does it decide whether to turn left or turn right? How big does the robot need to be to make the turns? How fast does the robot need to go down the lines? Also, how are you going to hook it all up? How is it going to be powered? There's a bunch of different questions that we need to ask ourselves. And with that, there are many different solutions. Luckily for us, IEEE, that's the Institute of Electronic and Electrical Engineers, is hosting an annual event. They've been hosting it since 1970, called the Micromouse Competition. Now in this competition, teams compete by having designed and built a micromouse. That is an autonomous robot that should be able to navigate through a maze, map it, and calculate the fastest and shortest distance through the maze. Now enough about why we're here. I'd like to hand it off to Ronnie to explain who we are.
That's right, folks. So as my colleague was saying, we needed to ask ourselves lots of questions to make sure we had a successful micromouse at the end of this. Now, luckily, a team of dedicated engineers have come together to find a solution. Ladies and gentlemen, I'd like to introduce you to the Robotics Allied Engineering Division.
Hello everyone, my name is Roy. I'm an electrical engineer and I'm working on the hardware.
My name is Patrick Monterre. I am a computer engineer and I was dealing with the software side.
Hello everyone, my name is Ronnie Offman. I'm an electrical engineer and I'm working on the hardware side.
My name is Joshua Fernandez. I'm an electrical engineer, and I also work on the software.
Hello, my name is Foster Maraz. I'm an electrical engineer and I also supported the software team.
Okay everyone, now that you've had a chance to meet the team, I'd like to present to you our flagship product, Sensors. The sensor empowered navigating 10-scale labyrinth solvers. Now this isn't something that emerged overnight. We needed to set milestones and goals for ourselves to make sure that it turned out perfect. And to talk to you more about that, I'd like to turn it over to my colleague, Fausto.
Like any small or big project, you have to have some goals and some milestones. We set some milestones. On October 20th, we needed to complete a prototype 1, or preliminary prototype. At that time, we had schematics, layout, mounting brackets, and software. By October 30th, we needed to complete phase 1 of our software. We implemented 90-degree turns, 180-degree turns, and also made some decision making and obstacle detection. As you can see in the picture, we had our prototype 1. As a second picture, we had our phase 2 of the software implementation. At that time, we had to have constant acceleration, deceleration, and acceleration on our prototype 2. We also made modifications on prototype 2 on November 10th. We had to make modifications to create the second rev of our PCB. And at that time, as you can see, here's our second prototype. On our final revision, we had to implement and integrate all the software that software team came up, all the modifications on the hardware, and create our final product. Luckily for all of us, we were 1 week early. We had a goal of December the 3rd to do the final testing. We completed it. We had it ready to go. Let me show you a short video. You see us traveling around the maze real quick, give you a little glimpse of what it does. As you saw our previous competitor, they had it running right through them, right? And now let's go a little bit on all the technical side, all the specifics and everything. So I'm gonna pass it up to Ronnie to talk about motors.
All right, ladies and gentlemen, there were a number of approaches we could have taken in starting Sentinel, but we decided to start with the motors. The motors we chose were 2.8 volt, 1.7 ampere phase step-up motors. These motors were rated at 200 steps per revolution, which gave us approximately 1.8 degrees per step in the circle of rotation. To power these motors, we chose to go with a Texas Instrument chip on a breakout board, a blue loop breakout board. What was special about these drivers was that it gave us the ability to run 2.2 amps continuous while supplying it with 32 microstepping capabilities. Now, these two combinations opted for a great and reliable way to get around any micromouse maze. In terms of sensors, we used sharp proximity sensors. These sensors were special to us because they offered us a sensitivity of 2 to 15 centimeters, which is very important when you're working in close proximities. In addition to that, they had a 16.5 millisecond refresh rate, and they had an output voltage of 0.4 volts to 2.5 volts, which would be fed into a ACD conversion pin on our microcontroller. But we'll talk more about that later. Now that I've discussed several components involved with Sentinels, I'll turn it over to my colleague Poon, who will talk about the power supplies.
Thank you, Ronnie. So Sentinel can avoid the strongest motor or the sharpest sensor, but it wouldn't come to life unless we provide it with our heart. So we decided to pick the LiPo battery 11.1 volts with a capacity of 1600 milliamp hours, more than enough to power in the maze for within 10 minutes. Another reason that we picked this battery because of its perfect dimension, 89 by 34 by 20 millimeter. It fits perfectly behind the motor. As you can see in the tree diagram here, the power source 11.1 volt range out to 3 different sections. Section number 1 is we use the voltage regulator LM2937-3.3 so that we can step down from 11.1 to 3.3 to power the PIC. The second section is we use the voltage regulator LM7805 to step down from 11.1 to 5 volts so that we can power the analog sensors. The last section is for the motor driver. It requires at least 8.2 volts, so that's why we feed it directly to the power supply. The next thing I would like to talk about is the user interface board. So this board serves 2 specific purposes. Number 1 is to debugging and programming the PIC chip. It integrates onboard programming so that it reduces the programming time dramatically and reduce the probability of damaging the PIC chip. The second purpose of this board is for selecting mode. It houses 4 different LED and 4 different push buttons. Each button runs different mode. We have run, speed, map, and brake. These constraints are given by the software team for the hardware team to implement. So now I'm going to turn over to my colleague Fausto to elaborate more on this.
So discussing with hardware and software and getting the constraints and requirements they need, we came up with some requirements. And in these 4 sections, we needed a GPIO, an analog digital converter, a UART, and also memory. The GPIO was to control the motor drivers, select the direction, and so the PIC that we wanted had that. It also had the ADC where it can grab an analog signal and digitize it for us and encode, make case statements of what it needs to do or what it's on in front and the side or the left or the right. Also, we needed a UART in order when we're debugging and understand what the behavior of the robot's going as it's traversing through the maze, we can see the output on a computer or a laptop. Also, we needed memory. We needed enough memory density in order to capture all the data that's coming back, feeding it into the algorithm of the maze, and capturing all that data. And so the PIC that we selected was PIC 32MX250. It was enough for our needs. To just cut the flow of the code, I'm going to pass it on to my colleague Josh.
All right, so as mentioned earlier, there is a user interface board on Sentinels located on top of the motors, and he has 4 different buttons. The first button I'd like to go over is the brake button right here. So the brake button, it resets the drivers to the motors and ceases all function. Now this is great for when we need to pick up Sentinels or if he's driving up a wall or something. The next button is the run button, going from the user interface down to the run button. Now, at this point, Sentinels has two options. You can either press the mapping button or let him go through the maze and just do a free run. If the mapping button is not pressed and goes through their free run, it'll go to the speed selection. That's where the third button is, the speed button. Now this button is going to allow the user to toggle through 3 different speeds. For simplicity, we have them as slow, medium, and fast, slow being default. So if no button is pressed and Sentinels goes through the free run, he's going to go through the maze and not record anything. If the mapping button is pressed, the Sentinels is going to go through the maze at a default speed, and it's going to update the path and register the walls and get all the mapping data each way to the center. Now, whenever Sentinels gets to the center, if he checks if all the data, or about 90% of the data of the maze is collected. Otherwise, he'll just go back and explore more. If it does meet that threshold, it's going to go back to the center and do a speed selection. Now, ideally, for the competition, we want that to be the fastest speed. And when we hit that speed button, Sentinels will run through the maze at the fastest setting and to the center. To talk more about navigation and the flood flow algorithm, I'm handing it over to Patrick.
Thank you, Josh. So before I get into the aspects of how we use the algorithm to do mapping and solving, I wanted to show you guys the actual demonstration of Sentinels navigating through a maze. So, and the functions that we use. So as you can see, our little animation is you see it's going down a straight path, but it's not necessarily going straight. You can see it's going left, it's going right. That right there is the method we call error correction. In this case, where it says the microcontroller is going to tell the motor drivers and the motors themselves to either increase or decrease the frequency, so, or in a general sense, to either speed up or slow it down. In that case, we were able to make sure it doesn't hit the walls either on the left or the right. Another function that we were able to implement was 90-degree turns, either left or right. And in this case, it made it saw a sensor, a wall in front, wall on the left, and it made a right turn, made another right turn, made a left turn. So now, when it gets to this point right here, it sees there's no wall in the front and there's no wall on the right. This is where the mapping and the solving comes in, and it has a decision to make, whether it can go straight or whether it can go right. So it's going to update that inside the memory. Once it does that, it's going to go straight. It's going to see it. It's going to go to a dead end, which basically means that it's going to be a bad area. So it's going to make a 180-degree turn. It's going to go back, and now in the memory, it's going to say, don't go back to that spot. Now it's going to go back to the other open area of the maze. That's going to keep going. It's going to go and see the area, make a left, another left turn, and then it sees another dead end. So now, once it goes back to the original spot it was at, it's going to map it as that's a bad area also. From there, even though it maps it sees that it's going back to the original spot, it's going to see that there's another wall open too. It's going to go back to that one, and eventually that sees that's the center of the maze. Once it does that, it's going to go back to the center or the starting point, and it's going to switch to map or solving. Once it does that, the user has the ability to set the modes to either slow, default, medium, or fast. And it's going to go basically from the start to the center in a relatively quick time. So now I'm going to show you guys a video of our Sentinels actually navigating a portion of the maze. So as you can see, it's going along the maze, it's making lefts, making right turns, and it's going straight. On the last part, you can see that it's moving left and right. That is the error correction to prevent it from hitting the walls. And going on to the actual algorithm itself, like a lot of people will be decided to use the flood algorithm. The three things that we wanted to get to accomplish from this algorithm is to find the bad areas, the good areas, and the shortest distance to the center of the cell. So the flood fill itself, how it works is when we start from the beginning, it's going to flood the maze with an array of bytes. These bytes correspond to the distance from the farthest part of the cell to the center. So now how is it going to know that it's this where it starts is going to be the center, or how is it going to know it's part of this? Well, as it's going to go along the wall, it's going to traverse, and it's going to update, keep constantly updating, and it's going to change those array values. Those byte values, when it starts, it's going to have around, like, so the farthest one is going to be 16, the one in the center is going to be 0. So as it keeps constantly traveling, it's going to keep updating not just that specific part of the maze or specific spot on the cell, but also the ones around it. So, and then from there, it's going to basically go through the entire maze and update the array values inside the memory block. Once it does that, like again, it's going to go back to the center of the maze, say that the maze is been mapped completely, and then they're going to select the inputs, slow, medium, fast, and then it's going to go to the speed run. Once they push the run button, it's going to go the shortest distance from the start to the center of the maze. So now, even though we have a great product and we have all the great components, everything comes with a cost, right? So I'm going to turn it back to my colleague, Kong, to actually elaborate more on the cost.
So given with a budget of $600, we have successfully assembled Sentinel within that budget. So the majority of our budget comes from locomotion system and microcontroller. 35% went for power supply, navigation system, and hardware. That leaves us 5% for incidental, which means if anything breaks down, we would be able to replace them. This project would not be able to come to life without the sponsorship of the especially the department.
That's not gonna overheat.
And especially Department of Computer and Electrical Engineering. We would like to thank John and Mark for helping us and mentoring us during this period of time. So we would like to invite you all to come to competition on December 4th and design day on December 5th. And last but not least, thank you all for coming.